When you look at a real-world network, such as my Facebook network, it's clear that the nodes with high closeness are close to other nodes with high closeness. That is, they're kind of in the middle, in the thick of things. And in general, we may want a definition of closeness, a separate centrality measure, which we're going to call eigenvector centrality, um, which says that you are as important as your neighbors are, and your neighbors are as important as their neighbors are. So it's this nice recursive definition. So if we have node I and we have its neighbors and the weights of the edges, then the importance of I is going to be the sum of these kinds of terms where we take the weight of that edge, and normally it's one, but you can use weighted networks as well, times whatever the centrality of that node is. And you may iterate this many, many times because, of course, as you're calculating the centrality for I, it's going to actually now affect the centrality of k, etc. And this is precisely the problem of solving for the eigenvector of the adjacency matrix with eigenvalue 1. And that's why it's called eigenvector centrality. One of the first people to apply eigenvector centrality to social networks was Bonacich. He wasn't happy with just, the plain adjacency matrix. He wanted a parameter that he could vary, and he chose this parameter beta. And what beta does is it says, how important is it that your neighbors are important versus just how many neighbors you have. So he was able to tune that. And this parameter alpha here is just a normalization constant. So you have that the centrality of node I for a certain parameter beta is the sum over all of its neighbors, which you're going to get from this, the adjacency matrix. This can be weighted or not. And for each of those neighbors, you're going to have this factor of alpha plus beta times the eigenvector centrality of the neighbor. And this can be solved through a matrix computation to derive the eigenvector centrality scores for all the nodes. Now, you don't have to sit there and calculate this by hand. That could get really hairy. And naturally, a lot of software can calculate these kinds of things for you, but it's good to know where it comes from, what the idea behind having such a centrality measure is. And so if you have small beta, what happens is, beta close to 0, is that only your immediate friends are going to matter. So it's going to be how many friends you have as opposed to how important they are, because their importance is derived from the structure of the wider network. If you have high beta, you're going to have low attenuation, meaning that all of those multiple steps are going to be quite important. It's not just how important your friends are, but also how important their friends are, the friends of friends of friends, etc. And in the case that beta is 0, you're just recovering the degree centrality, because all you have is the sum of the edges for a node. The interesting thing that Bonacich started examining was what happens if beta is actually negative. So when beta is positive, the centrality follows the intuition I said, which is that having neighbors who are themselves important makes you important. However, if beta is negative, nodes have higher centrality when they're connected to actually less central nodes. So let's see if this made sense to you. Take a look at these two networks and try to figure out which one has beta positive and which one has beta negative. So far, with the exception of degree, where we had in degree and out degree, we were talking primarily about undirected networks. And I just wanted to take a little bit of time to talk about centrality in directed networks. There naturally are many different directed networks, for example, the World Wide Web, and we mentioned how, the meaning of out degree, how many different pages a page points to, is really different from the meaning of in degree, how many pages point to it. So out degree just indicates, okay, is this page referencing a lot of different content? In degree is a signal of how many other people found that content relevant, enough so to link to that page from their page. Food webs, naturally directed, right? The wolf eats the sheep, not vice versa. Population dynamics, where individuals migrate, right? Migration patterns are usually directed. Influence, how much you influence someone is probably different from how much they influence you, and it depends on your relative prestige and the nature of the relationship. Um, Hereditary networks, citation networks, biological networks, such as transcription regulation networks or neural networks, are also directed. And it makes a lot of sense, right? If you have a task to do, then some nodes are going to affect the behavior of other nodes, and the network is directed. If it was undirected, things would be just firing back and forth. Some of the measures are just naturally extended into their directed counterparts. So if you remember when we talked about betweenness, this was simply the number of paths between all the other pairs of nodes that pass through our node of interest divided by the total number of paths that those pairs have. And what we're going to do is we're just going to change it. We're going to say instead of undirected paths, these are going to be directed paths. And when we normalize, we're going to have here n minus 1 times n minus 2, and we're going to lose that factor of 2 because getting from A to B can in fact be, or actually here from K to J, can be different than getting back to K from J. Right, so we do need to take into account the directionality of the path, but pretty much directed betweenness follows its undirected counterpart. Same thing with closeness centrality. You can talk about in-closeness or out-closeness, and typically you will only consider vertices that are reachable. So this is kind of getting, because once you have a directed network, it's even more difficult for everything to be connected, because if you have the same number of edges and they're directed, you're in fact, and you can only traverse them in one direction, right? You have about half the number of edges. So perhaps you're only calculating closeness for from the reachable nodes. And here, you have the kind of input domain are going to be all the nodes that can reach you. And the question is going to be how many hops does it take? And kind of the output domain are all the nodes that you can reach in an outward fashion. So again, it's very easily extended. Where things get really, I don't know if interesting is the right word, but where there was really a big game change when you added directionality to eigenvector centrality. And this was applied by Larry Page and Sergey Brin when they were graduate students at Stanford to the web. They just said, we're going to figure out how important each web page is, and we're not going to take just the number of other pages that point to it. We're going to instead look at the importance of those pages in a recursive way. And so, for example, here, at least at that time, /dot was really important. Lots and lots of other pages pointed to it. So it was enough for /dot to link to mention another page, and oftentimes that web server would just be brought down from all the traffic and attention that would ensue. And so we really want to capture this. It's not just random web pages that link to you, but whether those pages themselves are important. Now, there's an analogy here, which is that when you're calculating this eigenvector, it's as if you're doing a random walk. And so I like to think of it as a drunk who's kind of like wandering around, and every time he hits a node, he says, oh, okay, I'm just going to turn left and turn right. And so he's just following edges at random. And what PageRank, being the amount of time that he is going to spend at each node, what it then corresponds to is the eigenvector of the adjacency matrix. But there's a very important tweak. If this network, say the web, was undirected, the drunk could just kind of, go no, dip, 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 and then just go back the same way if he gets stuck somewhere. But when the network is directed, he can only follow the edges in a certain direction, meaning that here, if there is a cycle of this sort, he would just be trapped and circling here indefinitely, which then means that you actually can't compute the eigenvector, right? Because your random walker, your drunk, is actually being absorbed in different parts of the network. So the very cool insight that these two guys, Page and Brin, had was to allow for random teleportation, which is that with some probability the drunk is going to follow an edge when he arrives at a node, but with 1 minus that probability, he's just going to teleport to a random node in the graph. And this solves the problem of getting stuck, but it still captures this, the important pages are the ones that are linked to by important pages. So great. So let's see what this would look like on a simple toy network. Let's say the random walker starts at node 1. At the next step, he, with some substantial probability, will go to either 7 or 8, but we also have a 20% teleportation probability, which means that the 80% of going to 7 and 8 will be evenly split between them. So if we start out with 10 units to distribute, we get 4 each at 7 and 8, but we also distributed 20% evenly among all the nodes, including node 1. And so after the first step, we have most of the probability being at 7 and 8, but also he could have teleported elsewhere in the network. If we go on and look at what happens after 10 steps, you find that there's a lot of probability around 7, and this indeed makes sense because 7 not only has high in degree, but some of those nodes like 2 and 5 and 6 actually have other nodes feeding into them, and so recursively 7 should have high page rank. To check your understanding, I'd like you to go to this PageRank demo where you will be moving a slider to adjust the teleportation probability, and then you're going to iterate. So you're going to distribute the probability kind of like with each step that the random walker might take. And then I'd like you to figure out whether higher or lower teleportation probability leads to more equal or less equal distribution of PageRank centrality scores. Just to wrap up for now, we've seen lots and lots of definitions of different centrality values. We had degree, we had betweenness, we had closeness, we had eigenvector centrality, and we even had sort of network-wide measures of centralization. Does everyone have approximately the same degree, or is it really skewed? We extended this to directed networks. To see, when direction matters, how do these centrality metrics translate? And what might be missing from all of this actually is an understanding of, what is this good for? I mean, sometimes it's true. It's just nice to look at a network and say, oh, here are the central nodes. For example, you can do this with the Enron email network that was released as part of the court proceedings. And you can infer who the top level management was simply because of their high centrality. And it's not entirely trivial because sometimes the very top people don't email the most. Sometimes the people who are very central are the ones who kind of handle email on their behalf or are in charge of their calendar. So there are lots of interesting things to explore if you want to do exploratory data analysis. But if you are, oh, and I should say in the assignment, you'll be looking at actually a court case network, and this was an antitrust case where um, several turbine and other kind of power generator equipment manufacturers were accused of basically colluding, doing price setting. And the question is, how does an individual's position in this collusion network correlate with their probability of, or actually their outcome, that is, whether they were convicted or not, and how heavy their sentence was. So that's kind of cool, right? If you could ahead of time figure out how things will play out for a conspiracy network. The other paper that you'll be looking at is, well, it's this remarkable data set that Sinan Aral and Marshall Van Alstyne collected of personnel in a headhunting firm. And what they discovered was that it didn't matter how fat your Rolodex is, that is how many people's addresses you know, that it's in fact your positioning in the network, the diversity of your contacts, having less constraint that correlates both with your performance, that is how much money you bring into the company, and interestingly, with the information that reaches you, whether you find out new information more quickly than your colleagues do. So I hope that those two papers, which will be part of your assignment, will be interesting. And in the next video, what I'll do is just talk about some research I've done and how I've made use of centrality measures in a very practical way.